review the DFS. So DFS is like this. First, we start the DFS at U, and then V, Y, X, backtrack, finish, backtrack, finish, backtrack, finish, backtrack, down. And then select another white vertex and restart the DFS. Discover, finish, finish. Okay, this is what I said on Wednesday. And I explained the predecessor subgraph is a depth first forest. First, I'll explain an important theorem, parenthesis theorem. So I'll define a gray interval. Gray interval means it starts when it is discovered and it ends when it finished. Then the gray intervals of vertices are either inclusive or disjoint. That means assume that we randomly selected two gray intervals of two vertices. And then the two gray intervals, either one includes the other or they are disjoint. It means there is no overlap like this. That's the meaning of this theorem. And if one gray interval includes the other, then the including gray interval is the ancestors interval in the predecessor subgraph. Okay, this is the predecessor subgraph. Then the gray interval of U is the largest, and then V is included in U, and that of Y is included in that of V and X. And the gray intervals of U, W and Z have the same property. Why is this true? 박종훈, 박근배, 김범진, 장영민, 배민희, 신지수, 박준규, 최소리. Yes, perfect. So let's see the case of U and V. U is the parent and V is the child. Then, so because U is the parent, U is discovered earlier than V, right? So the discovery time of U is earlier than the discovery time of V. Okay? And because it is the DFS, V should finish earlier than U. Okay? It means V is discovered later and finishes earlier. So the gray interval of U includes the gray interval of V. And the same logic applies to V and Y. So between ancestors and descendants, the inclusive property holds. And if they have no such things, then they are disjoint like this. There is no overlap. Okay, look at this. If it is discovered, this one, let's say this is the gray interval of A and this is the gray interval of B. And A is discovered and B is discovered before A finishes. Then it is impossible for B to finish later than A. So that's why we cannot see these kinds of overlaps. Okay. And I said there are two kinds of edges, tree edges and non-tree edges. But non-tree edges are further categorized into these three types: back edges, forward edges, and cross edges. So tree edges are basically the edges used in these trees. And try to understand the meaning of these non-tree edges. From descendants to ancestors. So look at the tree edges. They are from the parent and to its child. But back edges are from descendants to ancestors, plus the self-loop. So they are back edges. 신경식, forward edges to its child, this is a tree edge. This is a forward edge. So from ancestors to descendants among non-tree edges. Okay? So tree edges are between parents and child. The forward edges are from grandparent or grand-grandparent to grandson or grand-grandson. So more than one step. 어미송, cross edge. Yes, that's right, but there is another case. In this case, this edge is between two different trees. But if the tree is like this, what is the type of this edge? Is this a back edge? No. So it's not from descendants to ancestors. Is this a forward edge? No, they don't have any ancestor and descendant relationship. So it is also a cross edge. Okay, so first, tree edges are edges in the trees. And then back edges are edges from descendants to ancestors and the subloop. Forward edges are from ancestors to descendants among non-tree edges. And all the other edges are cross edges. Okay, then let's get back to the DFS algorithm. And this time, we're going to classify the edge types. Okay? So we can easily determine them using the colors of visited vertices. If a vertex, okay, we are exploring the edge U to edge from U to V, and then V's color is white. Then what is the type of this edge? 권다운. 김현준. Okay. If V is white, the type of edge UV. Tree edge, yes, because the V is discovered at that time, the edge is a tree edge. How about when it's gray? When it's gray, it's a back edge. Why? Gray means ancestors. So at this time, U is discovered, V is discovered, but they aren't finished. Okay? And then, okay, Y is finished. Then when it explores a new edge, then there is some gray vertices. It means they are discovered and not finished. It means they are ancestors of Y. So it is a back edge or itself. And if it is black, it is either a forward or cross edge. So to determine whether it is forward or cross, we have to use the gray intervals. Because if it is a forward edge, one gray interval is included in the other gray interval. But if it is cross, they are disjoint. Okay, let me explain this using an example. Okay, this is the same example. Okay, 1, 2, 3, 4. So there is nothing special up to here, so I skipped all details. And then look at this. So V is gray. So this is a back edge. Gray means V is an ancestor of X. Okay? And then finish, 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 finish. And this. What is the type of this edge? So let's compare the gray interval of U and the gray interval of X. Then this includes this. Yes? So this is a forward edge. And backtrack. And then we select this. Okay, this. This is a cross edge. Y. 차정민. 김병준. 손혜성. 손혜성. 왕재민. Yes, they are disjoint. W is discovered after Y is finished. So the intervals are disjoint. So this is a cross edge. And then 3 and back edge. I explained the self loop is a back edge, but we don't check if it is a self loop or not, because this is gray. We can easily say it is a back edge. Then back. Okay, done. So I explained there are 4 edge types in a DFS forest. 3 edge, back edge, forward edge, and cross edge. And this is true for directed graphs. And let's consider a DFS of an undirected graph. Then there is something amazing. There are only 2 types, tree or back edge. It means there are no cross edges and forward edges. Why? Okay, in this case, first I will define the edge type. So, in an undirected graph, you can follow this edge this direction and this direction. So you can explore an edge twice. So, if you explore this direction first, and if it was a tree edge, and then if this was a back edge, the first exploration determines its type. The second exploration is useless. So keep that in mind and try to understand why these 2 edges don't appear. So then let's think about the forward edge first. When does it happen? Let's get back to a concrete case. Okay. This is the forward edge. Then this is a directed graph. Okay? Then first think about an undirected version of this graph. Okay? Then is this edge still a forward edge? What would it become? 박종훈. 박종훈? 박근배. What would it become? It's not a yes, no question. Okay, this is a directed graph, and assume a undirected version of this graph. Then we do the same DFS on the graph. Is this edge still a forward edge? 김범진. 장영민. 배민희. 박준규. 최소리. Three? 김종빈. Baggage, yes. Look at this. 3, 3, 3. But if it is undirected, you can explore this direction. Okay? So then it's a baggage by definition. So that's why there is no forward edge. Okay? Then let's think about the cross edge, like this. What would it be if it is undirected? 신경식. The cross edge, what would it be if the graph is undirected? Baggage? Okay, you had two choices, 3 or bag, but you were unlucky. Look at this. So in the traversal, and assume that we went this way, and then and backtrack. So at this time, we can explore this edge in this direction. So it becomes a 3 edge. So there is no forward or cross edges because they happen only if the edges are directed. And the running time of DFS is theta of V plus E because we visit every vertex once and every edge once in a directed graph and twice in an undirected graph. Okay. And I will explain an important application of DFS. It's topological sort. We are given a DAG, directed acyclic graph. And we have to generate a linear ordering of all vertices such that all edges go from left to right. Let me explain using an example. This is a graph. So the rounded rectangles are vertices and arrows are edges. So is it a DAG? 손광훈. Is it a DAG? Yes. There is no cycle in this graph. Then it is possible to sort all the vertices in a way that all edges are from left to right. It's possible. And let me explain how we can do it. Okay, first, let's look at this graph carefully and try to understand the meaning of this graph. So when you explain a graph, you should explain the definition of vertices and edges. What are the vertices? Yes. 순서. Order. Constraint. So vertices are clothes, undershorts, socks, watch, or clothes, or accessories, ties. And edges are order constraint. You should wear socks before you put on shoes. And you should put on shirt before you put on tie. Okay? And then this is a linear order such that all edges are from left to right. And there are multiple linear orders. This is an example. Look at this. First, we put on socks, and then on the shorts and pants and shoes and watch. Quite strange. Imagine a person with these parts on. Quite strange. And shirt, belt, tie, jacket. And do you put on clothes in this order? I don't think so. Especially the shoes first. So this is a Western style. We put on shoes last. So, okay, then let's develop a simple algorithm to topological sort of all vertices. How can we make this order? Even though it is inefficient, okay, think about a naive algorithm. Your idea is this. We successfully place a node from the left with 0 in degree. Okay? So look at the vertex socks. It can be placed in the leftmost position because it has no incoming edge. Okay? If a vertex has no incoming edge, it can be placed at the leftmost position. So we first select a vertex. Because it is a DAG, it doesn't have a cycle, we can find at least one vertex without incoming edges. In this case, there are several of those vertices on the shorts, socks, watch, and shirt. There are 4 possible candidates. Among them, in this case, it selects socks. And then an important thing is we should remove this edge from the DAG. That enables shoes to be the second leftmost position. Okay? And then we have still 4 possibilities. In this case, undershorts is selected, and then 2 edge connections are disconnected. Sorry, shoes wasn't my mistake. Shoes wasn't activated because of these 2 incoming edges. So there were 3, and undershorts are removed, then pants is enabled. So in this way, we can successfully find a vertex with a 0 in degree, and then we can sort all vertices. It is simple. But the problem is a naive idea takes non-linear time to do this. Okay, what is the running time of this naive idea? What is the running time? Cheongjun, what is the running time of your idea? N squared, right. V squared. Every time we select all vertices and then find a vertex with a smallest 0 in degree. Or if we use a heap, then it can be better. But still, it's V log V. So we can do it big O V time if we carefully choose a data structure. But there is a simple algorithm using a DFS. This algorithm, we run DFS, and after the DFS, every vertex has its discovery time and finishing time. Then we order all the vertices from right to left using increasing order of the finishing time. Okay, you look at this example. This is the result of the DFS. So try to guess the visit order of the DFS. 한상현. Okay, which vertex is visited first? Shirt. Okay, then tie, jacket, tie, belt, shirt. Okay. 1, 2, 3, 4, 5, 6, 7, 8. And then 강인구. What's next? Watch. Yes. Then undershorts, pants, shoes, pants, undershorts, and finally socks. Okay. That is the order of the DFS. And there can be other search result. But no problem. Okay, then we order the vertices according to the decreasing order of finishing time, or from left to right, or from right to left in increasing order of finishing time. Then the topological sort is completed. Can you understand the idea? Why it works? So we can think of another algorithm, this. So we can place a node from the left with 0 in degrees. But we think it differently. Then we can successfully place a vertex from right to left with 0 out degree. So first we place a vertex with 0 degree, and then disconnect all incoming edges to this vertex, and then find another vertex with 0 degree. Then let's think about the vertex with the earliest finishing time. So this X has the earliest finishing time. If it, because it has no outgoing edges, okay, it has the earliest finishing time. So that's why we can topological sort all vertices using the finishing time of vertices. So this is the power of the DFS. Actually, the original algorithm is the same as Yongjun said. Yes. Okay. But after the finishing time and discovery time ideas were developed, a lot of algorithms, a lot of problems has been solved by this simple DFS. They are strongly connected components and articulation point. A lot of problems was solved by this DFS. It was very powerful. Okay, I'll skip this correcting proof. Okay, there are some other self-study topics. Okay, I'll design some programming assignments. And it's time to show your talents and efforts.